Alrighty, folks. So given that it seems that a number of folks are going to need a little bit more of a reframing for predicate logic, what I'm going to do in this video is I'm going to go through and kind of give the reason why we use predicate logic when we're trying to symbolize complex arguments. And to start, let's start with this type of conversation. So let's say that I told you the following was true. All ducks are birds. We know that that is the case. If something is a duck, then it's necessarily a bird. Let's say that I also told you the following. Some brown things are in fact ducks. It follows then that some of the brown things out here in the world are, well, birds. If we were to use the language that we had learned earlier for symbolism, we would say we could symbolize the first statement, all ducks are birds, as, let's say, A. We would symbolize the second statement as B. And our conclusion would be symbolized as C. So when we look at the structure of this argument here, we see that it has an invalid structure. When we try to use what we call the scheme of abbreviation, the scheme that we learned for pretty much the rest of the logic so far in class, we find that we only get invalid arguments, even though when we reason through what's going on in this claim, let's go ahead and draw it out, we say that we have a box here, here's a box of ducks, the ducks are inside of the bird box, and then we're making a claim that there are some brown things that are ducks, some brown things within the duck box. We can visually see that it definitely is true that some brown things are birds. In fact, we would probably draw the brown box a little bit more like this, where the brown box just happens to overlap with parts of the things. But regardless, from the fact that we know that if something is a duck, it is a bird, and the fact that we know that some brown things are in fact ducks, it necessarily follows that some brown things are in fact birds. And yet, the scheme of abbreviation that we have so far for this class wouldn't actually allow us to show why that is true. So, what we do in this class is we introduce something called predicate logic. Now, what exactly is predicate logic? Well, predicate logic allows us to evaluate what we call categorical statements. So when we're talking about topics or groups of things such as ducks or people or philosophers or logicians, we're talking about a category of, well, people. And we can go ahead and break this into four main types of what we call categorical statements. So four types of categorical statements. We have a universal affirmative that says all S are P. And we could say something like all trees are plants here. We have a universal negative that says no S are P. So for example, no ducks are reptiles. We have what we can call a particular affirmative and that says that some S are P. For example, some dogs are in fact wolfhounds. And then we have a particular negative. And this says that some S are not P. For example, some dogs are not wolfhounds. This is going to be the structure that we use for figuring out symbolization, because we have a type of universal statement here, we have a not universal statement here, we have an exist X statement, and we have an exist, well, let me change the direction because we use the reverse C. We have an exist X statement, and we have an exist X statement that not. So when we think about how we symbolize different types of statements, let's consider first what we can call an atomic sentence. Let's do Plato is a logician. So what we have here is we have some particular being, Plato, and we have a category. The category is going to be something that we always give a large letter to. Since logician starts with L, let's give it an L. And then what we have next to the, in this case, the letter, is a placeholder. The placeholder can be a letter, it can be X, Y, or Z. It doesn't actually matter which one. And these just represents that you're kind of holding a place for some particular object out there in the world, even if we're not talking about that particular object. So if I was to tell you LX, I'm talking about the entire set of logicians. So there's an entire set of logicians, and I'm just talking about all of them. And we could point out like some particular logician here, there, but this also just represents the set. In contrast, when we look at Plato, what we find is a particular person. Particular persons get symbolized using little letters. Let's use little letter p to represent Plato. So if we were to try to symbolize Plato's logician, what we would write is we would write our category letter, and then we would substitute in the p for the x. So in this case, we need a way of symbolizing this sentence that reveals what we call a subject-predicate structure. This sentence says that a particular thing or entity, namely Plato, has a certain property or attribute, namely the property or attribute of being a logician. If we let the lowercase letter p name the individual, Plato, and let the capital letter L stand for the predicate is a logician, then we can symbolize the statement as LP. For our class, the capital letters A through Z are going to designate properties, or what I've been calling categories. They're going to represent sets. In contrast, what we're going to use with the lowercase letters, and we're going to use the lowercase letters A through U, we're going to use those to name individuals. Now, this doesn't have to be individual people. It just has to be some particular thing out there in the world that is referenced and is called out by the use of that letter. So the lowercase letters that we aren't using, though, so for example, notice I said A through U, so that means that we're not using V, W, X, Y, or Z. These are going to be called individual variables, if I can spell variables. These are placeholders. So go back and look up here at the LX. X there is a placeholder. It's holding the place of some individual person that could be slotted in but isn't. So let's say that I wanted to write the following instead. Let's say that I had the sentence, blank is Roman. I don't know how to fill in that blank. In fact, that blank space could be filled in with the name of any given individual. We could name some ancient Roman. I mean, we could name Livy. We could name Cicero. I was about to say Herodotus, but Herodotus is Greek. Who else is Latin? All of Pompeii. We could just name every single person in Pompeii. And if we were to slot them into that blank, the statement would be true. That person, that Pompeian, is in fact Roman. So if we place the name denoting somebody else in that space, for example, if I was to say that Dr. Weller is Roman, we could end up with a false statement. So this also shows that this has a true and false value. It can either be true or false. And let's use R to stand for is a Roman, and then let's use the little letter X as the placeholder to stand in for something or other could end up being Greek. And then we can substitute in particular things. So Cicero is Roman. Julius Caesar is Roman. Marcus Antony is Roman, etc., etc. So what we're going to find is it gets to a point that what we have to do is we have to go beyond just this mere symbolization. Why? Well, let's go back up here and take a look at this. So when we look up here, what we see is we're talking about all and some. When we talk about all and some, we're talking about some bigger category of beings, some bigger category of things. So let's consider the statement that everything is human. We can't really just say HX. Why? Well, that would represent the human portion, but what gets missing there is the everything. What we need now is to introduce something that allows us to symbolize what it is that we're talking about and what I would call the scope of what we're talking about. So we can indeed use HX to represent that X is human. And remember, X is a placeholder here. It's standing in place of some specific being out there in the world that is human. But what we need for the everything is what we call a quantifier. A quantifier is used to indicate how many things have that property or the properties in question. For example, all and some are quantifiers in English. They tell us how many things out there in the world have those properties in question. Either all the things do, none of the things do, some of the things do, some of the things that things have it some of the time. So when we consider what we had earlier, we saw that blank is Roman. Well, everything is one of the things that we can slot into that blank. We could say that everything is Roman. We would have a false statement. But everything and some also can fit into that blank. So what we need is a way to represent what happens when we slot those things into that blank. So let's go back to everything is human. What it is when we say that everything is human is we're saying that for any given individual thing X, X is in fact human. So if what we mean by everything is human is this, then we're going to want to have a shortcut way for representing for any individual thing. So what we do is we introduce the idea and the concept of what we call a universal quantifier. The universal quantifier for our system is X. And this means all X, or for any individual thing. So we could say it could be read as for any X, for all X, for each X, for any individual thing X. Pick your translation. This is why we need a universal quantifier. We need to be able to represent what happens when we slot in this everything into our blank slot, into our placeholder slot. So let's consider what happens now if we wanted to symbolize a universally affirmative statement. And remember, universally affirmative statements are of the form all SRP. So let's look at what we can call a universally affirmative statement. All ducks are birds. And we're going to use the symbolism schema of for X is a duck, dx, and for X is a bird, bx. So we have dx and bx. So let's start by rephrasing this universal affirmative. The statement says more or less in effect that if anything is a duck, then it is a bird. In other words, it says that the following expression is true for any filler that we place into the blank spaces. Namely, if blank is a duck, then blank is a bird.